Hello and welcome to the Acoustic Effectiveness of Vinyl Fence Noise Walls webinar. My name is Paula Hyman from the Ohio LTAP Center, and I'll be your technical support for today's webinar. Just a couple of housekeeping items. If you have questions throughout the presentation, please type them into the questions box and our presenter will address your questions during the presentation. There is one item available to download in the handout section, and if for some reason you're unable to download it, put your email in the questions pod and I'll send it to you directly. All documents will be emailed at the completion of the webinar to the group, and the webinar is being recorded. Provided that the recording is successful, the YouTube link will be emailed to all participants and uploaded to LTAP's website. Thank you in advance for your participation, and with that, I'll pass things off to Ms. Kim Burton with Burton Planning Services.
Excellent. Hi, everybody. Good to see you all. Just thought you could see my face here for a minute, and then I'll turn off the webcam just for connectivity challenges for everybody. But welcome to today's presentation on acoustic effectiveness of vinyl fence noise walls. And I look forward to talking to you about our research. All right, so before I get into the project, just want to introduce who the research team was. And so on the ODOT side of things, Jill Martindale with Statewide Planning and Research was our project manager. And then our advisory committee included Noah Cal of OES, Mark Carpenter of ODOT District 12, Eric Schneider, OES, and Keith Smith of ODOT District 8. Like I said, I'm Kimberly Burton, and I served as the principal investigator, and my team at Burton Planning Services served as the prime consultant. And then we also had Capstone and Associates as a sub-consultant on the team, and they led our construction management activities. So the topics we're going to cover today, first we're going to just give an overview of what the project was, and then we're going to talk about the research objectives and the approach we took. And then we'll get more in detail on the results and the conclusions and recommendations. Lastly, we'll talk about some of our implementation ideas, and then we'll wrap up. But before we get started with our first topic, I just want to ask a couple of poll questions so I can see who all is in attendance today. So here's our first question, and Paula is going to do the poll for you, but I just want to find out what sectors that you all work in.
We have about 60 or 78% of the people who answered, so just want to give you a couple of more seconds here. Peter. Here you go, Kim. So your results are up there in your screen. 69% public, 31% private, and 5% other.
Okay, great. And then just the other question is just wanting to know what your level of noise mitigation experience is. So are you new to noise? Have you been doing it a little bit, or have you been doing it for a while?
And 20% new to noise mitigation, 35% some experience, and 46% experienced.
All right, excellent. Well, that's really informative, so I appreciate everyone participating. So it looks like we have sectors and experience all across the board. And so I geared my presentation that way, so I'll just go ahead and get started then. All right, so first let's do our project overview. So the reason we did this project is because there are currently a variety of materials from which noise walls can be constructed, and concrete and fiberglass are the most widely used. in Ohio at least. But in 2012, ODOT did a research study to compare and test the different noise wall materials, but they didn't examine vinyl materials at that time. Additionally, when looking around, there really is limited research regarding vinyl materials used for noise mitigation currently. So this project aimed to determine the acoustic, aesthetic, and cost benefits of vinyl materials to guide future noise mitigation implementation strategies. So after considering numerous sites, we ended up settling on 3 to focus on for the study. So the 2 dots there in green, one was at Greene, Ohio, and one was in Richmond, Virginia. They had existing structures made of vinyl materials. And then the red circle there for Lima, Ohio, that was an empty site that we ended up constructing a brand new vinyl noise wall to test out for the project. So for our research objectives and goals, so the primary goal of this study was to evaluate the acoustic effectiveness, cost feasibility, and overall benefits using vinyl materials as a viable option for noise mitigation. To accomplish this goal, locally sourced vinyl material was constructed and tested as a noise wall. We picked an ODOT site up in Lima, Ohio, and it was right along I-75. And this is a photo of the wall that we built, and I-75 is there on the top of the photo, and you can see a couple of the noise meters there in the photo from when we did the acoustic testing there. So in addition to acoustic testing in Lima, Ohio, we also did acoustic testing at existing vinyl fences in Richmond, Virginia, which had the same material as what we used in Lima, and also in Greene, Ohio, which had a different material than what we used in Lima. And both Richmond and Lima also had nearby concrete walls, so we can get a good apples to apples comparison of noise impacts. So these comparisons help to determine the advantages and disadvantages of using vinyl materials as noise walls, and helped us gain a better understanding of available vinyl materials and the feasibility of the products to be used for noise abatement. The research also identified some construction best practices when using vinyl materials for noise walls. So here's a quick overview of the approach that we followed. For step 1, project management, that was just lots of regular meetings, and today's presentation was in this step. And then step 2, we did a pretty comprehensive literature search and evaluation of what we could find that had been done previously. For step 3 is where we performed the acoustic testing at the 3 locations, one of which we built the noise wall. Then for step 4, we performed a data analysis and some modeling on the acoustic testing results. Then from all that, we prepared recommendations and conclusions, and then drafted the report and fact sheet, finalized it, and then prepared a little research article for ODOT's newsletter. So those were the major steps that we followed for this project. To look a little bit more in depth at a couple of these steps, first for step 2, for the vinyl material literature search and evaluation, a literature search of existing research was performed to collect existing information on previous studies on vinyl noise barriers and to identify best practices that could be incorporated in this research project. So data on the vinyl materials was also collected from the manufacturers, including cost and production time. And then also additional characteristics and other related information on vinyl materials were inventoried and compared. In addition, we evaluated vinyl material characteristics against the noise wall requirements in ODOT's Bridge Design Manual in Section 800. For acoustic testing, we split it up kind of into 2 parts. The first one was building the test noise wall, and the second part was the acoustic testing. So when we built the noise wall, first we had to pick a site. And so we looked at a total of 16 sites around Ohio, and we evaluated them for construction feasibility. From this evaluation, we picked 2 sites. And but after some challenges arose at one of the sites, we ended up just building on a single site in Lima, Ohio. And that was an ODOT property, so we had easy access. It was right along I-75, so it was nicely located along a major freeway. And so that's where we ended up building our noise wall. So once the vinyl fence materials were manufactured and shipped to the Lima site, the construction contractor installed the vinyl noise wall following the manufacturer's installation specs. And then the professional construction management services led by Capstone staff and assisted by ODOT and us documented the installation process, best practices, and challenges observed during construction. So here's just some photos that were taken during the construction process. First, here's what the panels and posts look like when they were shipped to the site. So they were just shipped in these packages all ready to be assembled. And then here's just a close-up here of that package, so you can see the posts and the panel support brackets that were already attached to them. Here you can see the very first post has been installed, and then on the right side of the photo you can see the auger is being used to drill the hole for the next post. Here, this is a little bit later down the line. They're starting to clear dirt away from one of the post holes they've drilled. In this photo, you can see them installing the lower panel support brackets. And here you can see, they've got quite a few panels installed and they're adding concrete to the post hole. And so here are a couple of post-construction aerial drone photos we took of the new vinyl noise wall in Lima. So the first, you're looking south, so I-75 is there on your left, and the ODOT properties are on your right. And here's a second one, just looking from the other angle, looking north, and the ODOT properties on the left, and so I-75 is on your right. So for part 2 of our acoustic testing, the acoustic testing was performed at Lima, Ohio, along I-75, both before and after construction. So you can see the aerial here, the yellow line is the noise wall, and you can see the 5 meters. We'll talk about those here a little bit more in a minute. And then this was the nearby concrete wall that was just to the north that we also tested on I-75. And then in order to gather additional data, we conducted acoustic testing at 2 other locations. So we identified an existing vinyl privacy fence in Richmond, Virginia along I-675, or I-64. And then this is the concrete wall that was a little bit to the south, also on I-64. And then here's in Green, Ohio on I-77, there was a short vinyl fence at this property. And so you can see the yellow line there is where the vinyl fence was. And then we also tested a no wall location just to the north of the property. So we followed ODOT's noise manual and FHWA's noise measurement guidance on noise readings for the acoustic testing. We prepared noise measurement plans, and we contacted property owners and respective state DOT staff when needed in advance of performing the fieldwork and construction activities. In order to gather a meaningful amount of data and to account for site and traffic variations that can affect noise readings, each site included at least 3 rounds of 15-minute noise readings. And so I'll go back up here. So you could see here at this one, you can see the 5 meters pretty clearly. So we did 5 noise meters at most of the sites, where noise meter A is basically on top of the wall. It's 5 feet above the wall. And then noise meter B, which is right here, is 5 feet behind the wall, but they're at the typical 5-foot ground level that we typically take noise readings. And then C is 50 feet back at 5 feet above ground. D is 100 feet back, 5 feet above ground, and E is 200 feet back at 5 feet above ground. So the Green, Ohio site was a little more limited because the site was constrained. You can see the building is right here. So we were really only able to go 50 feet back at this site. Traffic counts on the primary roadways and ambient and meteorological conditions were also recorded during the noise readings. So I'm going to attempt to play a short drone video we took, just so you can see a little bit of movement here. So this is the noise wall we built in Lima, and so you can see right here, we're starting to see the noise meters. I'll just go back a little bit so you can see the meters. So you can see here's the noise meter that is on a pole, and it's 5 feet above the wall. And then this is noise meter B, that's 5 feet behind. Then we got C, and then D and E are off the screen here, but it gives you a good idea of kind of what the setup looked like when we took the noise readings. Sorry, it's a little choppy. I was afraid that would happen. So, see, back to the PowerPoint. All right, so for the next step, the data analysis and modeling step, the results from the acoustic testing were tabulated and we analyzed the data pretty in depth. So the data analysis used aggregated and disaggregated noise observations along with T&M noise model predictions to fully assess the acoustic effectiveness of the vinyl materials using multiple methods. So the different analyses we performed on the data included an aggregated drop-off performance comparative analysis, an aggregated difference in difference comparative analysis, and then a disaggregated minute-by-minute descriptive statistical analysis, followed by the T&M modeling, predictive analysis, and the cost-benefit comparative analysis. And we're going to talk about these more in depth in the next section. So after completing the data analysis and modeling, the final steps of the project included these last 4 steps. So for step 5, utilizing the findings and results from the previous tasks, recommendations and conclusions were prepared regarding the vinyl materials, including acoustic effectiveness of the materials, information for ODOT's list of improved noise wall types and suppliers, and ideal types of sites for the construction of vinyl noise walls. In addition, recommended best practices were prepared for the construction and installation of vinyl noise walls. For the draft report and for the report and fact sheet, first we prepared a draft and had that reviewed both by ODOT staff and a couple other state DOTs. And then we updated and finalized the report and the fact sheet, both of which will be available to download by the end of the week. Paula will send out a link shortly. And so then the last step was just preparing a short research article for the ODOT newsletter. All right, so let's get into the meat of the data here. First, we're going to talk about the empirical data analyses that we performed. The first one was the drop-off performance comparative analysis. And in this analysis, that involved the noise drop-off performance of various vinyl material and concrete material and no wall configurations. And the drop-off performance over set distances at the 3 sites was averaged for all 5 noise meters using about 37 field data observations and then evaluated to identify patterns. So you can see here in this map here that above was the pre-construction conditions at the Lima site and below was the post-construction conditions. And so we looked at these average LEQs at each of the meters and kind of evaluated what the drop-off looked like both pre and post construction. And then we did this for the other sites, understanding that the walls were already in existence at the other sites. So let's look at the results from these 3 sites in addition to a more in-depth look at the Richmond results. So this table shows the calculated average drop-off observations over distance where noise reading data was collected. Some of the data was contaminated due to various environmental issues such as birds and cars and a lovely year for cicadas, if you guys remember that last year. So we either omitted some of that data or we redid our testing. And that's where you see all those subscript letters popping in there is where we had those contamination issues. So looking first here at Lima, when comparing the pre and post construction noise levels, there was a large decrease in noise levels from noise meter A to B. The post-construction drop-off was steady from A to E, but wraparound noise due to the wall being only 400 feet long most likely affected the results at D and E, since those were the ones that were further back at 100 and 200 feet. Looking at the Richmond, Virginia wall, these sites best captured the performance of vinyl materials over distance because the vinyl site had the longest and tallest vinyl privacy fence that we looked at. And the other sites at Lima and Green experienced some noise contamination issue, or Lima experienced some noise contamination issues. However, this site did have some contamination issues due to the cicadas, so we actually went back at a later date and took more readings just to make up for that. Both the vinyl fence and concrete wall showed steady decreases in noise levels from A to E at Richmond, and concrete did outperform vinyl, especially at the closer distances. But at noise meters D and E, the 100, 200 feet distances, the performance difference was much smaller between concrete and vinyl, indicating that the concrete material outperformed the vinyl material within 50 feet, but at distances over 100 feet, the two materials mitigated noise by a very similar amount. All right, so let's look at a little bit more detail at Richmond. So this graph here shows the 60 minute by minute noise observations collected across noise meters A, B, C, D, and E. So these 60 observations per meter represent each minute of the 4 15-minute noise reading sessions. So you can see the 4 groups. These were each a set of 15-minute noise readings. And here the noise levels dropped by an average of 13.2 decibels between noise meters A and B. There was minimum average decrease between B and C, but those were pretty close together, so that makes sense. And then from meter A to meters D and E, the noise levels decreased substantially again by 15.8 to 20.3 decibels. So as you can see by the pretty flat lines on this graph, the noise levels didn't experience any major variations during the reading, so these were pretty clean readings. All right, and then looking at the green site, the drop-off performance couldn't be compared between concrete and vinyl using the collected readings since there wasn't a concrete wall nearby. But the T&M modeling predictive analysis did offer a performance comparison, which we'll discuss here in a little bit. However, drop-off patterns for the vinyl fence and the noise wall the no wall scenarios could still be evaluated. And so the vinyl fence showed noise reductions from A to B, but noise meter C was likely affected by the wraparound noise effects from the short vinyl fence length. All right, so now we're going to talk about the difference in difference comparative analysis that we performed. And so you can see here in this photo, this is the Lima site. So the top is our vinyl wall and the bottom is the nearby concrete wall. And so both Lima and Richmond, we were able to compare these concrete and vinyl walls nearby each other. So for a direct comparative analysis between vinyl and concrete, the methodology of difference in difference was employed using 23 field data observations. The difference in difference techniques captured the difference in noise level reduction for 2 treatments, the concrete and the vinyl, as compared to the control condition, and we set that as noise meter A, since that was located just above each wall and was fully exposed to the road noise without any other contamination. To isolate the traffic noise reduction properties of these different materials, an empirical analysis was initiated by focusing on the aggregate noise readings taken at noise meter A and noise meter B. This focus minimized the contamination by ambient noise and decreased the effects of variations in wall height, length, and distance from the edge of pavement due to the close proximity of B to the different vinyl and concrete structures. By measuring the difference in noise levels from noise meter A to B for each material type, and then taking the difference between those noise level reductions, i.e. a difference in difference, a vinyl performance coefficient was estimated, which is the observed noise level reduction performance of vinyl as compared to concrete. This analysis was able to be performed at Lima and Richmond, as I mentioned, because they both had the nearby concrete walls. So now let's look at the results of this analysis, in addition to a comparison with some previous noise readings that ODOT took. So this table summarizes the key details of the 3 sites. It estimates the acoustic performance of structures at each of these locations and presents the results of the analysis of the aggregate data for each wall type. The report contains a more detailed version of this table, so we're just looking at the highlights in this table today. So at all 3 sites, the vinyl materials produced substantial reductions in noise levels. The Lima and Richmond locations had the same vinyl materials, or simulated stone, And the green Ohio location had a different vinyl material, Tahoe 2. So in Lima, Ohio, the vinyl noise wall material showed a 13.5 reduction traffic noise from A to B. If you look over at Richmond, it had a similar performance, reducing noise by 13.0 decibels. At both Lima and Richmond sites, the concrete materials were more effective at reducing noise levels than the vinyl materials, with an observed average noise reduction from A to B of 17.7 for Lima and 16.8 for Richmond. The vinyl fence for Green, Ohio, although constructed of a thinner vinyl material, still performed well and reduced noise levels from A to B by 9.9 decibels. So translating that, my apologies. So translating that then is the coefficient. So to calculate a performance coefficient that directly compares vinyl to concrete, the average noise meter A to B decibel reduction for the vinyl material was divided by the average noise meter A to B decibel reduction for concrete. So the results show that the vinyl material, the simulated stone at Lima and at Richmond, achieved a 76 to 77% performance of the concrete material. So you can see the green, it's actually blank. There's no number there, and that couldn't be calculated because it didn't have a concrete wall. But we did estimate it later during the modeling predictive analysis section. So I'll show you that here in a minute. So one other thing to mention is the ODOT actually performed some acoustic testing before we did this project. And so when we looked at their past field work that they had conducted on vinyl materials, we found a similar performance for vinyl materials when calculated between A and B. And so they took readings at various locations around Ohio, including at Green, Ohio, and our results were the same. The results of the observations indicated that simulated stone vinyl material is outperforming other vinyl materials tested, and the findings were consistent with this study. So that was nice to be able to kind of compare and make sure we were on the right track. So now we're going to move on to the other empirical data analysis we performed, which was a descriptive statistical analysis. And this one was a little bit of, we were calling it internally extra credit, because it gave us a chance to perform a statistical analysis on the data because we could use a larger data set. So an analysis on the disaggregated minute-by-minute data from Lima and Richmond was performed in this analysis to examine the distribution of noise reduction performance in greater detail using 300 minute-by-minute field data observations to calculate descriptive statistics. And that's why I have this noise meter session report image here. So for those of you that are used to downloading these from noise meters, you know that you get a minute-by-minute LEQ for your 15-minute reading. So you get 15 sets of individual pieces of data. So that's what we did, is we actually extracted each of those individual pieces of data so that we had enough to run a full statistical analysis. We didn't do this for green, once again, because it didn't have a concrete wall, but we did go ahead and calculate a vinyl performance coefficient for this analysis and compare it with the vinyl performance coefficient we calculated from the previous analysis to see how they measured up. So looking at the results for the Lima, Ohio disaggregated data, these histograms show that the 75 disaggregated minute-by-minute differences in noise levels between noise meter A and B for both the vinyl and concrete walls in Lima, Ohio, were actually pretty clean data. So on average, the concrete noise wall reduced noise levels from A to B by 17.92 decibels with a margin of error of plus or minus 0.426 decibels. So in other words, inside a confidence interval of 95%, the actual mean noise level reduction falls within 2 standard errors of the sample mean. By comparison with the vinyl noise wall, that one reduced noise levels from A to B by an average of 13.53 decibels with a margin of error plus or minus 0.248 decibels. So these are there's not much deviation here in the data. And so the calculated vinyl performance coefficient for this minute-by-minute analysis was 0.76, which actually matches exactly and confirms the performance coefficient calculated in the earlier aggregate analysis for Lima. Looking at Richmond, these histograms show 60 minute-by-minute noise level differences between noise meter A and B for concrete and 90 minute-by-minute differences for the vinyl privacy fence. On average, the concrete noise wall reduced noise levels from A to B by 16.84 decibels, with a margin of error of 0.732 decibels inside a confidence interval of 95%. And the vinyl fence reduced the noise levels from A to B by 12.95 decibels with a margin of error of 0.151 decibels. So this was also very clean, and the calculated vinyl performance coefficient of this minute-by-minute analysis was 77%, which is again consistent with the performance coefficient calculated in the earlier analysis. So overall, the disaggregated minute-by-minute statistical results for Lima and Richmond confirm the findings from the aggregate analysis that simulated stone delivers the 76 to 77% of the performance of concrete material. So examining the field data across the sites in Lima, Ohio, Greene, Ohio, and Richmond, Virginia, several conclusions can be reached. First, the material used to construct Greene, Ohio, the Tahoe 2, did not achieve the same level of noise reduction performance as the material used at Lima and Richmond, which was the simulated stone. Second, the performance of the vinyl materials at Lima and Richmond delivered less noise reduction compared to concrete noise walls, but the materials were still about 75% as effective as the concrete walls. And third, the readings for the Richmond location at the more distant noise meters C, D, and E, where the noise readings were the cleanest compared to the other field locations, indicated that the 12-foot high vinyl noise wall delivered substantial noise reductions across the entire 200-foot distance behind the vinyl privacy fence, even when compared to the concrete wall. All right, so those were all the empirical analyses that we did. Now we're moving on to the predictive analysis that we did using the simulated data generated by T&M models. So this analysis predicted acoustic behavior for 14 receptors at the 3 vinyl material sites: Lima, Ohio with 5 receptors, Greene, Ohio with 4, and Richmond, Virginia with 5. So the receptor points were placed at the same locations at the 5 noise meters as what we did in the field. This approach allowed for the direct substitution of concrete noise walls at the same location of the vinyl materials, while other variables are held constant. The noise models could also calculate the noise levels at all the noise meters without the contamination issues that occurred with many of the noise readings. This approach allowed the research team to approach experimental control. So let's look at the results of these 3 sites. So at the Lima, Ohio location, the vinyl noise wall was constructed at 8 feet, so the concrete wall height was also modeled at 8 feet. So the results show that the 2 no-wall scenarios are similar and are within 3 decibels for all the noise meters except for noise meter E. And then for the concrete vinyl noise wall comparisons, noise meter A was calibrated within 0.1 decibels. Under these parameters, the model's predictions for the concrete noise wall shows a greater noise meter A to B noise reduction, 14.2 decibels, than does the vinyl noise wall at 13.5 decibels. Reduction difference is 0.7 decibels between concrete and vinyl, which is actually a smaller difference than we observed in the aggregate analysis, which was 4.2. In addition, as can be seen with the no-wall results comparison, T&M over-predicted noise levels by an average of 2.7 decibels. So from these results, a modeled vinyl performance coefficient was calculated at 0.95, which is much higher than the 0.76 coefficient calculated for the aggregate analysis. It's important to note that the percentage of trucks on I-75 was quite high. It was 35 to 38%. So T&M 2.5 can overpredict noise levels because the software attributes 60% of all traffic noise produced by heavy trucks at 12 feet high. However, based on what ODOT has currently been studying, there's actually little to no noise produced by heavy trucks at 12 feet in height. So it does appear that T&M may be overrepresenting heavy truck noise, But like I said, ODOT is actually currently conducting field studies to research this further. At the Richmond location, the vinyl privacy fence was constructed at a height of 12 feet, so that's what we modeled the concrete noise wall height at, and the results show that noise meter A was calibrated within 2 decibels. So under these parameters, the model's predictions for the concrete noise wall shows a greater noise meter A to B reduction at 16.4 decibels than does the vinyl privacy fence at 13.0 decibels. This difference of 3.4 decibels is just slightly smaller than the one observed in the aggregate analysis at 3.8. So from these results, a modeled vinyl performance coefficient was calculated at 0.80, which is just a little higher than the 0.77 coefficient calculated in the aggregate analysis. It's important to note that for this site, the modeled levels were overall less than the measured levels, hence the modeled reductions were overall greater than the measured reductions. At the Green, Ohio location, the vinyl fence was constructed at a height of 7 feet. So the concrete wall was also modeled at 7 feet. So the results here show that noise meter A was calibrated within 0.4 decibels. And under these parameters, the model's predictions for the concrete wall shows a greater noise meter A to B reduction at 12.9 decibels than the vinyl fence at 9.9 decibels. So comparison with the aggregate analysis couldn't be performed because of the lack of the equivalent concrete noise wall at this site. So from these results, a modeled vinyl performance coefficient was calculated at 0.77. However, as we saw from the other 2 sites, the model performance coefficients seem to be higher than in the aggregate analysis. So they were on average 0.11 higher. So if we reduced the 0.77 by 0.11, we could estimate that an aggregate analysis would put the vinyl performance coefficient at 0.66. Which would be expected given the difference in the vinyl materials at this site being less effective than the other materials. However, more research really should be done on this specific material to refine this number with empirical data collected from field testing. So to summarize the predictive analysis results, the modeled results are broadly consistent with and supportive of the findings from the empirical analyses. So here's our last analysis that we did. We did a cost-benefit analysis. So for this one, benefits related to the acoustic performance of the different noise wall materials were identified, and the material and installation costs of the vinyl and concrete walls were documented using data collected for this project and from the manufacturers. Then the cost per square foot were estimated and compared using data normalized for the year 2021. In addition, non-quantifiable benefits and costs were identified for qualitative factors. So this table illustrates the comparative and quantifiable acoustic benefits and costs of the different noise wall materials. So here you can see the vinyl performance coefficient for simulated stone, which was the one used at Lima and Richmond, was calculated between 0.76 and 0.77. These coefficients mean that this vinyl material is 76 to 77% as effective at mitigating traffic noise as a standard concrete wall. In addition, the Tahoe 2 PVC material, that was what was used at Green, that's estimated to be less effective than standard concrete wall and the simulated stone vinyl material. The disaggregated minute-by-minute analyses and the TINA modeling predictive analyses supported these findings. So according to the literature search, the ODOT Bridge Design Manual in section 805.1 states that the minimum accepted sound transmission class, or STC, for a reflective noise barrier is 30. The standard concrete wall exceeds a minimum of 30 at 45, and it has a panel thickness of about 4 to 6 inches. The simulated stone vinyl material in comparison is slightly less than the ODOT minimum with an STC of 26, and its panel thickness is about 2 inches. The Tahoe 2 and then an additional material called Augusta, which are very similar to each other, they don't have published STC data, but their panels are thinner than the others at 0.875 inch, so the STC is likely lower than 26 for them. Therefore, the STC and panel thickness data support the vinyl performance coefficient results. Standard concrete materials are outperforming the vinyl materials, but the simulated stone vinyl material is close in performance to the concrete, and the Tahoe 2 and Augusta materials have the lowest performance of all the materials. So the material and installation costs of vinyl and concrete were also documented and compared. For concrete walls, the 2021 combined material and installation costs were estimated at $35 per square foot for ODOT noise walls. For vinyl materials, the simulated stone vinyl material and installation costs were estimated at $19 per square foot for the Lima wall and $26 per square foot for the Richmond wall. The reason that these two are different, even though they're the same material, is that the Lima wall was 8 feet and the Richmond wall was 12 feet. And if you build the simulated stone walls over 8 feet, you have to use a more expensive post. And so that was the cost difference between the two. The Tahoe 2 PVC vinyl material and installation costs, which was the Green, Ohio site, were estimated at $14 per square foot. When comparing the vinyl material cost to the concrete material cost, the cost of vinyl materials are 54% and 74% for the simulated stone, depending on the height, as compared to the concrete materials, and 40% of the cost for the Tahoe 2 materials as compared to concrete. So they are significantly cheaper. So to summarize, this study found that the vinyl noise walls can deliver about 75% of the noise reduction performance of concrete for about 50 to 75% of the cost, depending on the height of the wall. So lastly, let's just discuss some qualitative factors that we considered. There are additional benefits and costs associated with noise wall materials that are not easily quantifiable, but they're still important factors to consider, especially because they may differ between the various noise wall materials. These factors have been identified through the literature searches and the findings of this project and include aesthetics, ease of construction, installation, construction time, cost of repairs, difficulty to make repairs, cost of maintenance, difficulty of maintenance, availability of source materials, durability and longevity of those materials, strength and wind load resistance of materials, and environmental impacts of source materials manufacturing installation. Preliminary findings from the study indicate that the vinyl noise walls are quicker and simpler to install and easier to repair and maintain, whereas standard concrete walls are more durable and can resist higher wind loads. When you think about aesthetics, the simulated stone walls can actually look very similar to concrete, but the Tahoe 2 and Augusta materials look more like fences. And then potential environmental impacts were outside the scope of study, and so those are currently unknown, but some of the vinyl manufacturers were claiming their products were green, but we weren't quite sure why. All of these qualitative factors may warrant additional study. So for the last part of our time here, let's talk about the conclusions and recommendations that came out of this analysis and then the implementation ideas. So first was really the main focus of the study was the acoustic effectiveness of the vinyl noise walls. So we define effectiveness as the degree to which something is successful in producing a desired result. And what we did is we took ODOT's feasibility and reasonableness tests and applied them to vinyl. So first is feasibility. How well did the vinyl materials perform acoustically? Did they mitigate noise enough based on ODOT requirements? And second, how feasible was it to install the walls? Are they cost effective and constructible based on ODOT requirements? With the simulated stone, it's mitigating traffic noise almost as effectively as standard concrete walls. Like I said, it's about 75% as effective, even though the STCs are lower than the ODOT minimum. So it's very likely that this vinyl noise wall material could meet ODOT's feasibility requirements for some noise sensitive areas, but probably not for as many areas as concrete walls. Thinking about reasonableness, the vinyl noise walls are substantially less expensive to purchase and install, but there are some constructability concerns, and they are not as durable as concrete. So recommendations to address these concerns, thinking about comparing the cost and the expense and maintenance, it's still going to be cheaper to build and maintain the noise walls, but you still have to think about durability. And we're going to talk about the constructability concerns here shortly. And then for aesthetics, the simulated stone noise walls can look almost identical to concrete noise walls, so there are really no aesthetic concerns for the simulated stone. But other vinyl materials like Tahoe 2 and Augusta, they really look like privacy fences, so that's just something to consider. So factoring in the discussion on the feasibility and reasonableness factors and aesthetics, the results do indicate that vinyl noise walls are an attractive and effective option for mitigating the impacts of traffic noise. So like I said, I mentioned there were some constructability concerns. So you can see this photo very clearly illustrates what the concern was. So we're just going to talk about that in more detail here. So we constructed the vinyl noise wall at the Lima site in July of 2021. And in mid-December of 2021, so just a few months later, the ODOT staff there noticed that the vinyl noise wall had suffered some damage. So you can see it here that it just bent, one of the panels bent basically completely vertically to horizontal. And then some of the posts right near there, it's kind of hard to see in this picture, but you can see this one, they're just a little out of plumb. And so we worked hard to try to figure out what caused the damage, and was it wind, was it weather? We talked to the contractor, we talked to the manufacturer, and did some troubleshooting. Apparently, according to the manufacturer and the contractor who've done a lot of these, they've never seen anything quite like it. We talked to 2 other owners of existing vinyl noise walls around the US, and they said they hadn't really seen this damage before. So in April of 2022, once things warmed up a bit, we were able to go out there and dig up this part of it and repair it and figure out what was going on. So for the posts, we found that the soil was very saturated, well below the ground level, and that indicated poor soil conditions and explained the post and the foundation movement. And then the dislodged panel here, it was found to be missing a steel reinforcement bar in the top portion of the panel. You can see here, this is completely empty and hollow, and there's supposed to be a steel bar that runs through here. And that was a defect from the manufacturer. So there was a steel reinforcement bar at the bottom of the panel right here, and that's why this thing bent in half and stayed in there and prevented it from blowing out completely. So the posts were reset, and the defective panel, the manufacturer sent us a replacement one with all the steel in place, and you just slide them in and replaced them. And we also just talked to the manufacturer and the contractor to really refine our best practices so that we can incorporate them into our recommendations for this material, because obviously this is not acceptable to build a wall and have this happen a few months later. So for our construction best practices, we organized them in the report by a few different categories. I'm just going to talk about some of the highlights here today. First, we're going to talk about equipment and material best practices. One of the main things here is mixing the concrete before placing it in the hole. You can see this photo here that the specs just say go ahead and dump the concrete in and add water and it'll set. And that's not necessarily wrong, but in this site location where we had the soil moisture issues, it would have been better if they had been mixed beforehand. We also noticed that the vinyl material really reacts to temperature. So they do expand and contract in extreme heat conditions. And so it's just something where when you're building this, it's probably good to store them in shade and to really monitor them during freeze-thaw cycles if you are in a part of the country that has winter, and just see if there's any gaps that occur that you need to address. In addition, we noted that since herbicides are often used along ODOT right away to maintain vegetation, we're not quite sure what those impacts would be. So it's probably good to either install them away from the edge of pavement or at least monitor any effects. In addition with like salt spray applications for the winter months. for best practices related to process, just a few to highlight here. So each panel has a 4-inch and a 2-inch border along the 8-foot edge of the panel. The 2-inch edge of the bottom panel should butt against the 2-inch edge of the top panel when they're erected. So that's per specs. So butting the flat ends next to each other should always be done to help reduce the potential gaps. And then pre-digging of all the post holes, even though it's more efficient, it kind of could compromise the quality of the installation. So it's really better to dig the holes as you put the panels in, just to make sure you're adjusting for the distances properly. And then lastly, for spoils, there were quite a few spoils that came out of the post holes. So it's good just to keep them, and then you can reuse them if there's any gaps along the bottom of the panels on the ground to backfill there. In addition, we noticed that the top of the panels and posts could be held more consistent if the ground line under the bottom of the panels were actually trenched 4 to 6 inches in advance prior to drilling the post holes. And then although this is really the big one, although the simulated stone manufacturer specs do not include soil testing in them, ODOT has a requirement that a subsurface investigation is performed for all noise barriers. And so we highly recommend that soil testing be performed for vinyl noise walls, even though they're not in the manufacturer specs. And then, of course, regular inspections, especially since this is a newer material, just kind of keeping an eye on it and making sure it's settling okay and standing well. We actually had some recommendations for the manufacturer too, where we just mentioned that we noticed that there can be gaps a little bit here and there. So to look at maybe more of a tongue and groove fit between the panels versus just laying them on top of each other. We also noticed that there are some burrs left over from the manufacturing process, which had to be shaved down in the field. So having the manufacturer do that in advance would make things more efficient. And we also looked at when putting the brackets in, that the self-tapping screws could have been better designed just to make it more efficient to use them. And then lastly, one of the things we definitely noticed is the post caps. Right now, they're only installed with a friction fit, and it probably would be better if there's some other attachment method that makes them a little bit more secure for wind issues and other issues. And then we have our ideal sites. This is the last part here where we really tried to look at, especially since we considered so many sites around Ohio to build a wall on, we really wanted to identify what were the best places for these vinyl materials to make them the most successful. So first, finding something that is relatively flat is better. So the way the vinyl materials are installed, if the site is at least somewhat flat, it just makes it easier for the installation. It's also good to avoid sizable obstructions, whether they're on the surface, underground, or above ground, which is also kind of typical for regular noise walls, but still worth mentioning. And then I use this photo here so you can see the right-of-way fence is on the left of the center of the photo, and the wall we built was on the right side. And it was really important that we left sufficient space between the noise wall and the right-of-way fence so that maintenance was easy. We initially recommended that the noise wall, the vinyl noise wall, shouldn't be constructed too close to the roadway to prevent roadway debris and snow and herbicides and salt spray and all that from damaging the wall. But it turns out the Richmond, Virginia wall, it was constructed on the edge of shoulder behind guardrail about 9 years ago, and it's still in really good condition. So we may not need to worry about that as much. We also, considering what happened with this site, the vinyl noise wall really should not be constructed in sandy soil with high water content as determined by soil testing prior to construction. And then also just wanted to note that if other ideal site conditions are met and the vinyl noise wall is feasible and reasonable, but the concrete wall is not during a traditional noise analysis, then the vinyl noise wall should be considered as a viable option for noise mitigation if there's appropriate funding available. All right, so we'll talk just a little bit here about implementation. So the results of the research we felt can be used to guide future noise mitigation implementation strategies because it really offered ODOT a better understanding of available noise materials and their feasibility for use of noise abatement. In the future, there's possible of offering more communities less costly noise mitigation options, thus providing more noise mitigation options to more people while potentially saving taxpayer dollars. As a result, end users for this research could be other state DOTs, engineers, planners, environmental specialists across the US are interested in more noise mitigation options. For further research, a few things we identified that I want to highlight here. We thought that more testing could be conducted to determine the STCs for the Tahoe 2 and Augusta vinyl materials. It also could be useful to research the comparative life cycle impacts on the environment between vinyl and concrete. And it could be beneficial to continue to study the vinyl noise wall constructed at Lima to monitor its continued performance and durability. In addition, installing more noise walls in different locations made from different vinyl materials could allow for more testing. And lastly, it would be helpful if T&M could model different noise wall materials. So additional research could be performed to study a vinyl material option in T&M. And we came up with 4 possible integrations for ODOT's noise program. First, one option would be integrating into ODOT's existing noise program. So ODOT could approve the stimulated stone material as an approved noise mitigation material, update their bridge design manual to permit it, using it, meeting certain standards, and then offer it as an option to the type 1 and 2 programs, just with a lower cost per square foot, but also a factor to reduce the acoustic effectiveness at the receivers by about 75 to 80%. However, consideration of the more effective concrete noise wall should still be given the priority before vinyl noise walls, so there aren't concerns that people are getting noise walls that are lower quality or less effective. We also talked about maybe a new program where there could be a new noise wall program that's separate from the type 1 and 2 programs, but supplements the programs. That could be almost like a second chance program for noise sensitive areas that don't qualify for type 1 and 2 types of options, but we need funds to be set aside for that kind of a program. Another option is just ODOT could choose to offer the vinyl material information as an option for local communities and neighborhoods to consider for themselves, even if they don't qualify for type 1 or 2, since these are pretty easy to construct. And then lastly, just, special projects, ODOT could elect to use vinyl fence noise walls just on a case-by-case basis for a type 1 or 2 project. All right, so to wrap up, today we covered quite a few things. We talked about what this project was, what our objectives and approach were, what the research results ended up being, our conclusions or recommendations, and then some of our ideas for implementation. Just some quick resources here. This is ODOT's noise program webpage. They've got a lot of good information posted here. And then also wanted to mention, like I said at the beginning, that the report and the fact sheet will be able to download from ODOT's site shortly later this week. And we'll provide a link to all of you that attended today to be able to get to it once it's ready. And of course, just a reminder that the slides are in the handouts in the panel. So that's all I have. I know I only left a minute or two for questions, but just thank everybody for attending today. If you have any questions, please let me know. You can see my contact information at the bottom. You can always feel free to email me or find me on LinkedIn if you think of something later, but thanks again for attending. See, I'm scanning. For those of you left, I'm scanning the questions that were posted while I was talking. Let's see. Judy posted a couple questions here if you're still with us. Let's see. Yes, I was trying not to overload. So Judy asked about barrier insertion lost information. I was trying not to overload the PowerPoint today, but yes, all that is in the report. And for cross sections of the site, I'm trying to think. We didn't really show cross sections of the sites. The sites that we all picked were very level on purpose so that we wouldn't have any, or we'd be able to minimize the elevation issues with what we were doing. Let's see, from Keith. Keith asked about the depth of post holes. I actually do not remember what the depth of the post holes were. We followed the specs. And I do believe that based on the soil testing, we would recommend something probably a little deeper than what the specs gave us, especially considering the saturated soils that we experienced. And then Keith, you also said higher quality of vinyl windows incorporate aluminum inner to be, yeah. Yeah, it's a good point that maybe there could be something added to the panels to help with thermal shrinkage. Good point. And then let's see, Keith also said, do manufacturers offer a vinyl skin to overlay on damaged concrete? That's a cool idea, Keith. I do not know. I'll have to look into that one. It sounds like another research project. All right, and then Missy Pear had a couple questions if you're still with us. Can you talk about the difference between this this vinyl noise wall and a vinyl fence? So Missy, yeah, I didn't get into detail on that. So basically everyone like to call their vinyl mitigation something different. And so for Richmond, they were very clear that it needed to be described because it was installed as a vinyl fence. Green was also installed as a privacy fence for the development. So we installed the vinyl material for as a noise wall. So that's why we were calling that one a wall and the other two fences. But the terminology is really interchangeable because the structures are not different. It's just how they were installed. So we were trying to be considerate of that. All right, and then Missy also asked, do you have any theories about why the simulated stone material is more effective than the other vinyl? With the different materials, really the simulated stone is the thickest and the most robust of the materials that we looked at. So you can see like on this photo here, this really looks like a concrete wall and it's quite thick. And let me go back to one of the earlier slides. Let's see, right here, this is the Green, Ohio wall. It really looks like a fence. It looks like a fence you put in your backyard. And so it's thinner. It's not, the panel itself is thinner, the material is thinner. So it's just intuitively not going to mitigate noise as well. Yep. Right. And then let's see, Judy had a question here. You mentioned that TNM overpredicts based on heavy truck noise, but some of the results show a couple. Yeah, the Lima site is the one that had the significant truck percentage compared to the other sites. The other sites, the truck percentages were not as high. So it's something that ODOT wanted us to point out is that with TNM and heavy trucks, there are some discrepancies in the prediction levels. So that's why I wanted to mention that specifically for Lima. Okay, Paul, at what temperatures did the heat begin to affect the vinyl? That I don't believe that's something that we observed too much when we were installing it. It's just something that we heard from other people that had installed vinyl walls that is a concern, that if you store it out in the higher temperatures, it will expand. So I don't have a number off the top of my head though, Paul, and I can check on that for you. Right, Gary, does the vinyl wall meet ASTM 53459 rigid PV? I do not know, Gary. That's something I can look into and let you know if you want to share your contact information. Okay. All right, Missy, again, let's see. So you mentioned a scenario where the concrete isn't feasible and reasonable where vinyl is. Yeah, so what we're saying here is if we're performing a feasible unreasonableness test using just TNM like a normal noise study, and we're just not quite getting to the numbers we need to meet the minimums of cost and number of residents is mitigated, then we can look at substituting a cost of the vinyl noise wall because it'd be cheaper, but we'd also have to somehow manually reduce the effectiveness. And that was the 75 to 80% that I mentioned, because we know that vinyl is performing at about 75% of the concrete wall. So this is not an exact science that we've refined for this research study, but it's something where we, on a case-by-case basis, especially, ODOT could look at saying, hey, we're really close on concrete, but we're not there. So if vinyl is half the cost, and is mitigating about 75% as effectively, then maybe we can thread that needle and get them a vinyl wall. But I'm not going to put words into ODOT's mouth for that. It's just in general, that's what we were talking about for ideas. All right, excellent questions, everybody. I appreciate it. All right, Paul, would anyone be available to work with me to trial a vinyl overlay repair to a damaged concrete wall? That is a very cool question, Paul. If you could share your contact information, I bet ODOT, Noel Calla especially, we could chat about that and see what ideas you have there. Thank you, Keith, for the original idea too. All right, Gary, is there a spec for deflection? I am not sure if the specs had anything about deflection in there. I would have to look. The good thing is we have all the specs downloaded, and they're included in the report in the appendices, so we can look at that. All right, Rolando, what is the manufacturer standard maximum height? Are those posts available at 12 feet from the manufacturer? Yeah, no problem. I really skimmed over this. So basically, for the simulated stone, if you're 8 feet in height or lower, there is a kind of less robust and lower cost post that you can use. But if you go over 8 feet, the manufacturer recommends I believe it's a steel post with a vinyl lining on it, and those are more expensive. I don't remember the max at the height that those walls can be built. I know that obviously I mentioned that Richmond was 12 feet, and I can't remember how high it can go past 12 feet, but I can look that up and check into that for you. And that would also be in the specs in our report. Okay, and Missy, do you know how vinyl performs regarding graffiti removal? That's a very good question, Missy. We didn't test that out. That would have been really fun to test out on this project. But I think that if I remember in the specs, it's supposed to be very graffiti removal friendly because it's a very slippery surface, especially compared to concrete. But I don't remember specifically, but I do believe that they said graffiti is pretty decently easy to remove. Yep. Wonderful. I really appreciate all the great questions, everybody. Thank you. All right. I don't think I missed any. Any other questions that anyone would like to share? Okay. Well, like I said, for the few of you that I wasn't sure on the answers, please feel free to reach out with your questions and we can get back to you. And then also once the report and fact sheets are ready to download, there'll be a lot of that information will be in the report for you. Wonderful.
All right, thank you so much. I will send out that link to that report with the follow-up email because we did have one person ask about that. So
Mhm.
thanks again for your time today, and everyone have a good day.
Great. Thanks, everybody. Bye.